Good evening, everybody, and welcome to the 5th Annual Astronomy Lecture here. Our speaker tonight comes from Iowa State University, the Department of Astrophysics and Astronomy there, and he is a guest of our class here at MCC's, our astronomy class, introductory astronomy class. He, by the way, teaches an astronomy class in the introductory level at Iowa State, but his research work is certainly more deep than that, I can guarantee that. Dr. Russell Lavery is here to my right. He is an assistant professor in astrophysics at Iowa State, and he's published extensively in the field that he's going to talk about, and other areas of endeavor also. And he's had teaching experience at the college and the high school level. He's had experience in the Peace Corps in West Africa, teaching physics. And that is his expertise. His general fields of investigation is observational studies of galaxies and clusters of galaxies, interacting galaxies, and galaxy evolution, and high-resolution imaging. And the topic of tonight is gravitational lenses. So he has done work there, and he's going to tell us all about gravitational lenses this evening. So please welcome Dr. Lavery from Iowa State University. Dr. Lavery.
Thank you. I always open with UFO slides. Just a habit for some reason, because everybody would like there to be UFOs. But I just use them for focus. So tonight, what happened already? Okay, I'm going to talk about distant galaxies seen through something called gravitational telescopes, and the title had to change a little bit because Roger wasn't certain if we should use gravitational lenses. Gravitational telescopes are not something that are built, but something that you have to find out in space. But I'm going to give you a brief description of how we find them, what they are, and then also how long ago they were first found. And that was only really about 10 years ago, the first examples. Okay, so, and that's me, Russ Lavery, Department of Physics and Astronomy. I have to say, we're not astrophysics yet. We would like to be, but the physics people kind of push us around. And then we have at Iowa State University. Now, unfortunately, to try to get this topic started, I have to give you some basics. And I don't really want it to sound that much like a class. But in astronomy, there are lots of different types of objects out there. Okay? Most of the objects that people are used to looking at are stars. Okay? The sun is like a star. You know, all the stars that you see, it's just much closer, so we can see it in much more detail, but all those little faint objects that you see out in space are stars also. Okay? And stars are pretty heavy. I mean, we're going to be interested in talking a little bit about gravity, so we're going to be interested in how heavy objects are or how massive they are. And the sun's pretty heavy. It's about 10 to the 30 kilograms, so that's a 1 with 30 zeros after it. It's quite large, right? And because of the fact that it's large, it can hold all the planets around it. Okay? Now, using 10 to the 30 kilograms, or such a large number, kind of gets bulky in astronomy. So we don't want to use a number like that. And so instead of talking about kilograms or whatever, people usually talk about masses of stars and masses of the sun. So people use solar masses. And so when we talk about stars out in space somewhere, they range from 1/10 of the mass of the sun up to like 80 times the mass of the sun. Okay? So don't worry about the kilograms, but just make yourself familiar with the sun and you can compare that all. Okay? And if anybody wants to ask a question at any time, please do. I lecture every day. You know, I don't need to do it at night too for a hobby. So please, it would be great if you ask questions. Now the other astronomical objects that are out there and that are much, much prettier than the plain old stars, and I'll show you some pictures to show you the difference between these, is that there are things called galaxies. And galaxies are big groups of stars. When we talk about big groups, you want to take lots and lots of stars and put them together. There are little groups that are called star clusters, but bigger groups that seem to be isolated by themselves are called galaxies. And when we talk about galaxies, there are lots and lots of the stars that make up the galaxies. And so we can think of a typical galaxy, say the Milky Way, which is the object that we live in, has about, you know, this is about 1 trillion stars. Okay? Maybe it's 100 billion, somewhere in there. Okay? So it's pretty large, and it's a very massive object. Okay? Now, after that, I mean, so we have stars, and big groupings of stars are called galaxies, and when we take galaxies and make them into bigger groups, we have things that are called clusters of galaxies. And clusters of galaxies are some of the biggest objects that we know of in the universe. Okay? And so they are groups of galaxies. Sometimes there'll be thousands of these galaxies into one group. Okay? And so because of that, that's why I say that they're very massive. Because if you went through, you'd have 1,000 times this times that, and you can figure out how massive they are. They're very massive objects. And if you wanted to know the numbers for some reason, which I don't, but these clusters have somewhere around 10 to the 15 solar masses. So that's about, you know, 1,000 or a couple thousand Milky Way galaxies in them. Okay? Or so if you wanted to write that out in terms of kilograms, you'd have to write 1 with 10 to the, you know, 45 zeros after it. And a lot of people think astronomers really can appreciate those numbers or understand those numbers. Those numbers are really big. We're used to dealing with them, but that doesn't mean we can conceive them. Okay? So we write them down and we just accept it as a fact. Okay? Now, I mean, it is a large, when you get into these very large numbers, it just gets really messy. Does anybody know how long 1 billion seconds is? Anybody know? How many people think they lived 1 billion seconds? Yeah, it's about 32. Yeah, it's 32 years. Okay? So that's right. So anybody who's under the age of 31 point something, you haven't quite lived 1 billion seconds. Okay? And that's only, you know, that's something like this, right? That's only this part, and then you get, you know, another 1,000 of those, another or 1 million of those. So it's really quite, you know, these numbers are really kind of mind-staggering sometimes, and it's not like we go, oh yeah, we can understand that. We just deal with them. Okay? So 1 billion seconds, you know, if your nephew is, or your kid's giving you problems, tell them to count to 1,000, or count to 1 billion, and it'll give them a Milky Way candy bar, and let them go at it. And they'll be doing it for quite a while. Okay? But so these are large numbers. They're hard to deal with, but we're going to deal with them anyways. Okay? Now, I'm going to try to show some slides to show you what some of these various objects look like. Let's see what happens. Okay, there's a very simple one. We'll try this one. This is the sun. This is what a star looks like, but it's not really what all stars look like. This is the only star in which we can take a picture that looks like this. Sometimes the sun will look like this, and sometimes it won't. And we see sunspots. That's probably the most spectacular thing that we can see on the sun. Okay? So that's a picture of a star, but the only star that you can take a picture like that. Here's usually what you see when you see pictures of stars. Okay? Here's a cluster of stars, a group. You know, they're just little tiny points of light. And they're tiny points of light because they're so far away from us that we can't see the detail like we can in the sun. Okay? And this is another cluster of stars called a globular cluster, but all these stars are just tiny points of light, but they're all similar to the sun in nature. Okay? And here's a picture of a double cluster, H and Chi Persei, for amateur astronomers. It's you can kind of see this with naked eye, but it's very nice in binoculars. Okay? But stars are always little tiny points. And sometimes they have little dust clouds around them, like in this case here. Right? And this is a famous cluster called the Pleiades, which some amateurs people would find. Okay? Now, going away from that, there are things that are called galaxies, the ones I talked about, that have lots and lots of stars in them. And this is one of the most boring kind of looking galaxies around. This is called an elliptical galaxy. It looks kind of round in shape. But this galaxy here is one of the most massive ones that we know of. And it has around 10 to the 12 or 10 to the 13 stars in it. It's a very massive object, lots of stars. Okay, 1 trillion stars in it. Okay? Now, there are the galaxies that look like this, which is what most people recognize as galaxies. Okay? This is M81. It's a very nice spiral galaxy. It has lots of star formation in it. Okay? And the Milky Way galaxy, which is what we live in, probably looks a bit like this. Okay? So this, once again, has lots and lots of stars. And the sun is probably in something that's like this, and we're kind of way out here somewhere with the sun, right? Some little tiny point of light. And spiral galaxies make up the best astronomy pictures. Unfortunately, I'm not going to talk about those. But I did bring a couple. Okay. So this is another one where a nice pinwheel pattern that, once again, is kind of like the Milky Way. So these are all kind of like what galaxies are about. So they're very massive objects, but they're not the biggest objects out there. Okay? And sometimes they have these little bar structures and stuff like that. So there's lots of variety of galaxies out there. Now, the next one that I talked about was clusters of galaxies. And then when you start to take these galaxies, some of them are all out by themselves, but there are other ones that tend to be in groups and clusters, and that's why they're called clusters. And here's one of the nearer, close-by clusters of galaxies. It's in the constellation called Coma Berenices. Okay? And so there's these couple of very big, giant galaxies here. Okay? And these are about 10 times the size of the Milky Way, to what we're used to. And then all these little smudges, these kind of elliptical shapes. Actually, I have a laser pointer somewhere. I should have that. So basically, when you look at this picture, there's almost no stars in this picture, except, for stars that we're used to. This one up here is a star, and you can see it has these spikes on it, and that's what happens from a telescope. But all these other objects in here are galaxies, and this is a big, huge group that holds itself together by gravity. And all these galaxies in here are kind of similar in size to the Milky Way. So when you add that all up, you get lots and lots of galaxies, okay? Lots and lots of mass. Okay? And this is another one, and it's not quite as concentrated as the other one, but you can see there's lots of galaxies around. Anything that's not perfectly round is a galaxy. And then there are even more distant ones. This is, you can see these to very, very large distances. And so we have lots of giant elliptical galaxies, a bunch of little tiny galaxies, some spiral galaxies in here. And then we can even go to very, very distant ones. Okay? And that's why I'm going to talk about these clusters. When you look at this one, basically every little spot of light in there is something like the Milky Way. So if you try to put all this mass together, okay, it's quite there are, like I said, about 10 to the 15 solar masses all in this one little unit. Now this unit here, this cluster, is about 4 or 5 billion light years away. And they're useful for that because we can see them. When you put all these galaxies together, they make a bright spot. Okay? So this is the kind of object we're actually going to be talking about, or I'll try to tell you a little bit about. Okay? All right, now I have to do the classroom stuff. Okay, if we want to understand gravity, gravity is a very simple force, okay? And basically we would say that gravity is the force of attraction between any two objects, okay? And I can't tell you why that is, but any two objects attract each other, okay? And electricity, there's particles that attract each other and particles that repel. And, magnetism, there's a North Pole and a South Pole that attract, and the two North Poles will repel. In gravity, it never works that way. Any two masses that are out there, any two objects, will tend to pull on each other. And this was all put together by Isaac Newton, who is claimed to be the greatest scientist that has ever lived. Okay? And I'm not going to worry about the mathematical part of this, okay? We're not worried about that part, okay? But what's important when you think about the law of gravity is that the bigger the masses are, the stronger they're going to attract each other. And that's really the most important part of it. Okay? Now, when you work out this force, there's a little number in here, this big G. And that's a very, very tiny number. Okay? And because of the fact that it's such a tiny number, that even I wrote it out so I would remember. If I think of my fist, one of my fists is pulling on the other fist. Okay? And they want to try to come together. Okay? But the mass of my fist, how much weight is in there, is really tiny. Okay? So I don't feel it. Okay? Just like every other person in here, there's a pull due to gravity on every other person in here, due to all the people that are here. But that force is so small because of this number that's in here. Okay? It's really, really tiny. So you never feel it in everyday life. But when you start to think about the Earth, okay, the Earth has a large mass. And because it has a large mass, you can start to actually feel the pull of gravity. And you feel it every day. Okay? As soon as you stand up, and you feel your weight on your feet or what you feel on the bathroom scale. I've been trying to lose weight. I've been doing myself every day. When you go on the scale, it's because gravity's pulling on you, and it's the Earth that's pulling. Okay? So if you have large enough masses, then you can start to see these kind of effects. Okay? So if the masses are small, you're not going to feel it. But when you have big masses, then you can do things with gravity. Okay? And of course, I just went through showing you some of those objects because there are very, very big masses in astronomy. Now, the other thing that's kind of funny that I have to introduce, and I'm sorry this is almost turned into class and you should be taking notes, but this other thing that's kind of interesting, yeah, maybe I should have show you the pictures first and the theory next. But everybody's heard of E equals mc squared, okay? Or most everybody has. Okay? And this is kind of what makes nuclear bombs and everything else work. When you take a little bit of mass and somehow convert it into energy, you get a tremendous amount of energy out. Okay? But basically, energy and mass are related. Okay? Or that you can think of mass, like us, as a concentrated form of energy. Okay? And it's very concentrated because this number is very large, so you take a little bit of mass and makes a tremendous amount of energy. That's why the atomic bombs that are blown up, they could fit into this room, but then they would just blow up, everything else all the way out to Ames. Okay? Tremendous amount of energy. Okay? Now, for people who watch Star Trek, of course, you know that mass is just a concentrated form of energy because always in Star Trek, when people meet the most evolved beings, there aren't any massive objects with them. Right? The most evolved beings are those little spacey clouds that come around. Then they're pure energy. Okay? So that's the most evolved form. But mass and energy are related. And so someday maybe we'll evolve to become energy. But right now we're just mass. Okay? But E equals mc squared is a very important thing because energy and mass are kind of equivalent. Anybody want to ask any questions? I know, it's trivial, right? So, please ask if you're having any trouble. So the other thing I just have to tell you about is light. Okay? Because we're going to be talking about the bending of light by gravity, and that's how you make a telescope. You bend the path of light. Okay? Now, light is made up of little photons. Okay? So all these there's a bunch of little particles of light that come from the lights here, and that's what we detect in our eye. Okay? Now those photons move at the speed of light because they're light. Okay? And any particle that moves at the speed of light cannot have any mass associated with it. But we know that photons have energy. Okay? Visible light has energy. When you go to the beach, when you go swimming out here and you feel heat on your skin, those are infrared photons that are giving you the heat. Okay? And of course, ultraviolet photons are what make your skin turn red. Okay? And you also know that gamma ray photons and X-ray photons are really bad for you. That's why if you go to the dentist now, when you have X-rays taken, they put lead sheets over you. Okay? Because There's a tremendous amount of energy in the X-rays. And if your body absorbs X-rays, then it can do a lot of damage because the photon has a lot of energy associated with it and destroys things. Okay? So photons have energy but no mass. Okay? And so it's important to think of this E equals mc squared, okay, is that the photon has some energy, and you can think of it as a form of mass if you wanted to, okay? But it really isn't. But because of the fact that mass and energy are kind of equivalent, gravity is going to pull on the photon energy because it's energy, just as it would if it was a little bit of mass. Okay? And that's the most important thing. There's the mass. When you think of the mass of the photon, you would say it's really tiny because the energy is not very concentrated. But in astronomy, we still have these very, very big masses. And that's what's the most important thing. Okay? So out of all of this, the thing to keep in mind is even though there's no mass with the photon, there is energy, and gravity is going to bend the path that photons take, or the path that energy takes. Okay? Now, of course, this is very controversial, but it was actually first tested by looking at the sun. And this is a time when people used to go all over the world to look at eclipses. Eclipses were some of the biggest things around because they were very rare events, but they gave you a lot of information. Okay? And if you look at an eclipse, okay, that basically when you take, well, this is not going to work up very well. I won't even go through this part. Okay? But when you look at an eclipse, what they actually detected was the bending of light around the sun. And of course, you can't do that unless the sun is blocked out, okay? Because you can't see stars behind the sun, only during eclipse. And when they did, they compared it to a picture that was taken at a different time, and the star positions were where the stars were, and then when they took the picture with the sun, they saw the star positions were in different places. So as the light went around the sun, it was kind of bent, and we saw a different kind of distorted image of the stars. And this was basically done back in May 29th, 1919 by during a solar eclipse. Okay? And basically the most important thing that you can say is that when you look at large masses can change the direction that light is traveling. Okay? And unfortunately in astronomy there are these very, very large masses. And then I'm going to go to the slides in just a minute here. So the biggest masses in astronomy are these things that are called clusters of galaxies. Okay? Now this is a picture of a cluster of galaxies. And I tried to tell you that when you look at this picture, all these little black spots are objects that are galaxies, okay? Like the Milky Way. Okay? So there's this very, very big group. And this is some foreground stars that we don't have to worry about. Those are in the Milky Way. Okay? So there's about 10 to the 15 solar masses, and this cluster has two big galaxies in the center. This cluster is about 4 billion light years away. Okay? And the first picture that was taken that back in 1981 when this was first taken, they were kind of interested in this. I'll stop there. This kind of funny curve feature here. So this was only really, in 1981 someone noticed that and said, well, that's pretty peculiar. I wonder what it could be. I had no really idea. Okay? But it has a nice curved shape to it. Okay? So now I want to try the slides. All right, so I think I just keep going, huh? Yep. Okay, so this is a picture of that same cluster, okay, and you can see that curved feature, and in the next slide, we'll zoom in a little bit closer to it, okay. Now, so you can see the cluster here, and you see this curved shape to this thing. And what was puzzling about that when it was first discovered is if you figure that it's out there and it's a part of this cluster, it has to be about 300,000 light years across. Okay? So it's very difficult for people to understand how it could have that nice curved shape to it and yet be so big. Mm-hmm. This is another cluster of galaxies that was taken at around the same time. And so you see this central group of galaxies here and all these other galaxies around it. And now you start to see these kind of funny curved features around it here too. So this is another one which you start to see these curved features there. Okay. Let's skip that one. Here's another one that you see that it's a nice color picture that shows you the red galaxies and blue galaxies. But you can also see these nice curved features once again, some down here, some down here. And I'll show you another picture of this with Space Telescope. It's really spectacular. But it's these curved features that people started to get interested in. Okay. And here's another one where it's another cluster have these kind of curved images. Okay. So it was a question of what was producing those kind of images. This is another, these pictures are of the first two that were found back in 1986. Once again, this is the one that we've already looked at, this big curved feature. And then there was this other one here, had this big, almost halfway around some of the galaxies that are there. Whoa. Okay, this is a picture of another cluster of galaxies. I tried playing with red. It doesn't work very well. Okay, but almost everything in this picture is once again is a galaxy. And then we'll look at the central region here. So basically, all these little spots are these things that are like 10 to the 12, like the Milky Way. Okay. And if I look at the very central galaxy that's there, it starts looking like this. Okay. And when you look at it, you can see the big galaxy, but then there's a curved feature down at the bottom and this other curved feature at the top. Mm-hmm. Now, actually, this picture here I took when I was a graduate student. I did my graduate work at the University of Hawaii, so that was quite nice. But when I took that picture, I find it really quite puzzling. Okay? Because, you know, once again, how do you make these nice, smooth, curved features? And there are actually, this is how I learned to respect theorists. Back in 1964, this guy made some little models of taking objects and putting them behind other objects. Okay? And then what he did was to see how one object would bend the light from another object. Okay? And that's what this model is here. And I won't go into too much detail on it. But basically, here's an object, and he's going to move it to behind this object here. And then look to see what happens. Okay? And he makes these objects very massive, and because they're very massive, the light's going to bend around. If you want to look at the other way, you can start, well, let's do it this way. We put one object right behind another object, and because the gravity of one object pulls on it, it's going to focus the light back towards us from the object, and we get a nice ring. Okay? And as the object moves away, then you start to get arcs. Okay? And what was interesting about this picture is it looks really quite similar to something like that. Mm-hmm. Whoops. Yeah, that's not going to work, but that one looks similar to this one. Okay. So here's another nice blow-up picture of this. Let me zoom out. Okay, now this picture here is basically just to show that these curved features are actually very circular, symmetric around the center of the galaxy. Mm-hmm. So the center of the galaxy is here, and these circles lie around it, okay, right at the center, and you can see that this circle lies quite well. and this circle lies quite well here. Okay? So basically, when these are going to be produced, the question is, to make these up, they're going to have to be, what was thought was that they're going to be images of objects that are lying behind the clusters. Okay? So that this object here is not a real image and not a real picture of the galaxy, but it's a distorted picture of something that's lying behind this cluster. Okay? So the question is, how do you know if it's lying behind the cluster? And I won't go into understanding all these details about how to determine the redshift of objects. Okay? But basically, these arcs, these curved features, you have to measure how far away they are. And in order to measure how far away they are, we have to determine how fast the objects are moving. Okay? But basically, well, I won't go through the Hubble law. I think I'll skip that part. Okay. But what would happen is, if you take an image of these galaxies, then you measure how far away this one is. Okay. And I won't really go into the details of how you do that. But this object here and the cluster that's associated with it is about 2 or 3 billion light years away. Okay. And if you take a spectrum or determine how far away these objects are, they're about 7 billion light years away. So there are objects that are lying behind these distant clusters that are the light's being bent around them. Mm-hmm. Let's see. Okay, let's try to videotape now. Now, this videotape is going to be is a model of looking at one of these distant clusters. Okay? And there's going to be 2 parts to the tape. Okay? The first one is they're going to be taking, let me put these lights on first. Okay? The first part of the tape is going to be, you're going to take a random distribution of galaxies. And so when we talk about galaxies in this case, I'm talking about very, very faint objects, very distant objects. Mm-hmm. And then what they're going to do is they're going to superimpose a big mass in front of it. Okay? And they're going to let that mass grow bigger and bigger in size, and then you're going to see what happens to the background galaxies. Okay? So that's going to be in the first part. Then in the second part, they have, once again, they have a distribution of very, very faint distant galaxies out on the sky. Okay? And they're going to take a model of this cluster, this very, very massive object, and then they're going to just move it in front of these field galaxies, okay, these distant galaxies. And what's going to happen is you're going to see, as it moves along, the distortions of the light from of the background galaxies by these big, massive objects. Mm-hmm. And it'll do it a couple of times so you can kind of see them. And you'll see that when you see the field galaxies where they show you what they look like, you won't see any distortions, but then when you move this thing through, you'll see big arcs and rings and all types of other stuff coming about. Now, you think if I just press that one, huh? Okay. Oop. Here we go. Yeah. Okay, this will do it a couple of times. So this is one where they have the background galaxies, and you don't see the lens that's doing it, but you're just putting a more and more massive object in front, and you can see all these kind of curved shapes coming out. Okay. So once again, this is the, Okay, so that one, now this one gives you a little bit of details about, this is one I said where they're going to show you okay, these are the guys that did it. Tony Tyson, he's the one who sent me the tape. He's a nice guy. So this tells you a lot about, you don't really have to worry about the details of the cluster, this Abel 1689 and stuff. But basically, the important point is you're going to see the field galaxies, okay, which they talk about here, okay, and then how bright or faint they are. And then they're going to put a cluster of galaxies in front and then move it along, and you'll see different things happen to it. Okay? So this is the distribution of some very, very faint field galaxies. This seems to be on fast forward or something, but okay, the first is at high speed, second at low speed. All right. Okay, so these reds represent the galaxies, and all you're going to do is move the background galaxies across, and you can see all these distorted images and these rings that tend to form and come and go. Okay. So you can see if you watch them, especially coming out the backside, you can see what they start to look like normally when they come out this side. Okay. So you can see some of them like, whoa, you get these nice big rings. Okay. So once again, if you watch some of these galaxies come through, or as they leave, as they were big arcs, and they go through, then they'll get down to their actual little size that they should have been. Okay? So this is all because of these very, very big massive objects that are out there. Okay? So any pictures that we take of clusters of galaxies are kind of like a snapshot of any of this. I mean, we can't be moving the background galaxies or anything. So, you know, most of the time we'll start to see little images, little distortions, and then once in a while we can actually see some of the very, very big distortions that occur also. Okay. So if you watch some of these galaxies in here, they'll get, you know, they'll start to look kind of funny. And then watch these galaxies here, they'll start to move away and they'll take their normal shapes again. So you can, oh, here's a big, you know, nice big ring forming. And this is when a galaxy, that was a very faint galaxy, was right behind the center of the mass of the cluster. That's what happens when you get those big rings. There's just a very nice, perfect alignment. And you might be seeing another one coming here. And sometimes this image here and this image here are the same objects. I think this bright one's coming up pretty soon. So this one, which was a nice big image, is now just kind of going this nice little tiny galaxy. And I think maybe this is one that formed some of the big bright stuff. You can even see some images that are known as radial images, and these I can't even understand them myself. So you need a very good alignment to get that kind of image, and nobody's ever found those in real space. Okay, and here comes that galaxy out the backside. All right, so there are other models that people have made that kind of look like this, that show all the kind of distortions that you can get out of this kind of lensing by these galaxies. Let me take that down a bit. Okay. And this picture here shows you the Hubble it's a picture from the Hubble Space Telescope, okay, showing a cluster of galaxies in which you can start to see all these little distortions once again. Okay? So there's a cluster. Now this thing is, like I say, it's pretty far away from us. But all these little distorted images are galaxies that are much, much further away. Okay? So you can see these nice curved features here and here. And there's one faint one here. And there's lots of others that don't show up in this picture, unfortunately. Okay? So now the question is, what do you want to do with those things? Okay? How can we use this idea to help us? I mean, what we want to really try to do is use these distorted images to try to make what the galaxy actually looked like before it got distorted. So if I want to try to figure out what that galaxy looks like, we're going to have to figure out what the lens looks like. Okay? So this light is being bent around the clusters of galaxies and focused towards us. Okay? But it turns out that, and it's called gravitational lensing because it does focus light to us, and we get more light from the objects than if there wasn't any mass there. But it turns out that the lensing by a mass is a little bit different from lensing by glass. Okay? And now, your usual telescopes that people are used to, they have a simple lens inside, okay? And it focuses light. And everybody has, when they were kids, had taken magnifying glasses and burned somebody else with them. That's basically what a glass lens will do. Okay? It takes light from the sun or any other object, and it takes light in and it focuses it into a point. Okay? And that's really what a magnifying glass will do, and many ants have been burnt for that reason. Okay? But the important thing about looking at how this works is that you can see that the light that goes furthest away from the center is bent the most. Okay? When I look at the lens by a mass, or by a cluster, or anything else, okay, that turns out to be a little bit different. Okay? Unfortunately, the mass, the way the mass lens works is it's, that doesn't work. It tends to bend everything that comes the closest to the mass the most, and everything that's furthest away from the mass the least. And so it's not quite the same as bringing all that light towards the one point and making a nice image. Okay? Now the other thing is that's more complicated is trying to understand the lens, is that the lens, or this whatever's doing the bending of the light, you hope you can see it. Okay? But it turns out that it's not always that clear as being able to see everything that's out in these clusters. Okay? Now clusters of galaxies are very complex objects. Unfortunately, they're more complex than I really want to go into too much. Okay? But one of the great problems in astronomy is, if I look at this cluster, though it's a little blurry in there, is when I look at this cluster, there's lots and lots of galaxies in here. Okay? And all these galaxies are moving around. Okay? And because of gravity pulls on them, so they got to either fall towards the center, or when they fall in, they pass through and come out the other side. Okay? So there's a big, huge mass that's holding this thing together. Okay? And if I figure out how fast all these objects are moving, and then figure out how much mass is in the galaxies, okay, it turns out that this thing should not be around. Okay? The objects in this cluster move too fast to be held by their own gravity. Okay? So in astronomy, there's a problem known as dark matter, and sometimes you hear about it, it gets in the newspaper. It's just that a lot of the universe, unfortunately, is not able to be observed by astronomers. Okay? When I look at a cluster of galaxies like so, and I look at all the mass in these galaxies, I said there's lots of mass. Okay? When I look at the mass that's in the galaxies themselves, that's only about 1 or 2% of the mass of this whole cluster. And because of that, we can't see the mass, and it makes it hard to make a model of the lens, because if we can't see the mass, which is doing the bending, then it's a little bit trickier. Okay? So clusters, I mean, this dark matter problem affects everybody, unfortunately. but it's one of the big problems with trying to understand lenses. Okay? Now, as I just said, there's a lot of this missing mass in clusters. Some of it is actually, it's hard to believe, and this is why sometimes in astronomy, even though they have new instruments, they have to go out and look at objects that you wouldn't expect to see. Okay? Because in the 1960s, it turns out that when you look at a cluster of galaxies, they have a very, very hot gas associated with them. And this hot gas, you can't even tell it's there, okay? But this hot gas has as much mass as all the galaxies inside the cluster. Okay? So why is this important for trying to understand this? Well, if we want to look at what background galaxies look like, you really need to know what you're looking through. Okay? So I'll give you a simple analogy of what's going on. Okay? Everybody's been, I mean, I'm sure everybody's been to different carnivals or whatever else at the fun house. Okay? And you go to the fun house, and of course you can look at yourself in a mirror, and you can come out in some funny shape. Right? And the shape of this mirror here determines what kind of shape you're going to look like. Right? So I take this normal person here, send it through some mirror, and get some funny shape out. Okay? Now, in astronomy, it's kind of like the reverse. I mean, we have this picture here, okay? But we don't know what the mirror is, so we don't know how to make this. Okay? So, you know, if you have this image, maybe you think maybe that's what people look like, but we know that if we look at them through that funny mirror, they'll be changed, right? So the same thing happens when we try to look at what's going on for looking at art or trying to determine what those background galaxies look like. We know what the image looks like. We know what this looks like. We can take pictures of those arcs and see what they look like, but we don't really know what the lens is, and because we don't know what the lens is, we can't figure out what the source is. Mm-hmm. Or we're going to try to anyway. Mm-hmm. So you might ask, why do I want to call them a telescope at all? Okay? And so in order to do that, then we just say why we have, what are telescopes? Why call clusters gravitational telescopes? And basically a telescope is an instrument for collecting light and radiation, producing magnified images. Okay? And so will these clusters of galaxies meet that definition? Here's a nice picture, and I'll show you some other ones, of kind of what goes on. And why this kind of lensing is really quite interesting, even though it's pretty difficult. Okay? In this case, instead of using background galaxies in this demonstration, what they're going to use is a set of numbers that represents something that's very, very far away. Okay? And if I shine the light from these numbers through a massive object, the results become very distorted. Okay? But when you look at the distortion, what's important about this distortion is you can still see some of the information is there. Okay? So sometimes you get double images, like if we look at the 6, okay? We can see an upside down 6 and the regular 6 on this side. And so the 5s are distorted. There's a 4 and another 4, and a 7 is just a little bit distorted. I don't think there's another 7 on this side. Okay? Well, so what's interesting about it is even though the thing gets distorted, the information is still there if you can just figure out what this lens is. Mm-hmm. And another way to demonstrate this is an exercise I had a student do last semester. What happens when you take an object, or in this case he was going to be a little picture of himself, and moves behind a very massive object. Okay? So here he had, here's his picture here. Okay, so this represented the student. And what he did was just put a very, very massive object in the center here. Okay? And then he took this little guy who's much further away than the object and is going to move it behind this very heavy mass. And as he does, well, at this point we're just starting to see a second image. This little person was supposed to be inside this circle, you see. And as you go and move him closer and closer to the center, okay, the picture that you see of the guy is distorted, but you can still see the guy. Okay? And then as you get closer and closer to the center, the images get more and more distorted, but you can still see his arms, you can still see his head and everything. So if you can understand what's going on in the lens, then maybe you can work backwards and reproduce the ultimate. And so in this case, when it gets very, very close to lining up behind, then you get a very, very distorted image, and yet you can still see that person is still there. And then finally, if the little body goes behind, then you get something that looks like this. And so here's one head, and here's the other head of the two images, right? But even though, like I say, it's distorted, that information about the details or what the object looked like is there. All you really need to be able to figure out is what is the lens. And then once you do that, then you can work backwards and figure it out. So if I look at these images, okay, two things happen to them. When I look at background galaxies, is that the images get pushed away from the cluster, they get pushed away from the center, and they get distorted. Okay? But as I said, it preserves that spatial information. Now, one of the first models in which someone tried to do this, he basically tried to produce, wow, in one of the arcs, if you look at how bright it is, it has 3 bumps as you go along the arc. And basically their model was a simple little spiral galaxy. Okay? That when you take a spiral galaxy and stretch it out and distort it, you get a nice big image that's nice and thin with these brightness loops in it. Okay? But you know, nobody wanted to believe that model. Now, there are very few models in which it's actually been done and very good, but this picture is one taken by a space telescope. And in this picture, you can see these bright arcs, and what's interesting about it is you can see all this bright patchy stuff. And so once we can figure out the lens, which is what's in the middle here, then you're going to be able to pick out the background galaxy. And this is it's a lot more complicated than it looks, but I'll just show you some results that I just found today where someone's actually done this. Okay? And one of them had to do with this cluster that I showed earlier. It looks like this. Okay. So we have this big cluster of galaxies, and there's an arc image here, and one image here, and another image here. And what they've done is try to make a model of this lens, of this cluster, and push it backwards, and then try to come out with what the object looks like. And they come out with an object that looks like this. So these images here are supposedly the undistorted images that go to the different arcs up here. This one in A is up here, this one in C is down here, and this one D is on the opposite side. So what they've actually reproduced, once again, is something that looks like this. Okay, now you can see this a little bit better. If you look at the images, arc C is this one up here, arc A here, and arc D. And you can actually see this hollowness in the ring structure. So they actually think they've figured out that this galaxy looks like this. Has this nice ring structure to it. And what's most exciting about this ring structure is, I don't know, last year maybe Dr. Appleton talked about ring galaxies. And one of the ring galaxies that he works on is the Cartwheel galaxy, which looks something like this. Well, can't fit it all on here. Let's go like this. Okay. But what's interesting about this ring galaxy here is that this kind of ring galaxy is produced by a collision of one galaxy plunging right through the center of another galaxy. Okay. And the fact that one galaxy plunges right through the center produces this burst of star formation, and the rings propagate out. And so what's exciting about this is the first image that's reproduced of a background galaxy happens to be a ring galaxy. And so there's a lot of talk about these ring galaxies indicating that there's a lot more galaxy-galaxy interactions in the past. Okay. So this is, like I say, a very new field, and I'll just finish saying that, that gravitational telescopes, when you can figure out what the lens is, they're going to provide the most detailed images, because besides the magnification you get from any telescope, you get the magnification from the cluster itself, and it's stretched out. And then nature's mass lenses are very complex, but we'll be able to understand them, and eventually we'll figure out what these more distant galaxies look like. Okay, that's, I'll answer any questions that you would like to. Yeah.
Before we have questions, could I remind you, those who haven't signed the ledger back here, we'd appreciate that if you would do that. I think most people did, but if those who didn't, please sign it back there. Dr. Levin?
I got a feeling it might have been too complex.
I read about I've heard about a thing called the greatest factor in all the galaxies. Local group is kind of headed in that direction. Have they tried to take images through that to see?
Yeah, some people have. There have been some work to try to use, because the great attractor, they weren't really certain what that was. And for a while, some people thought it was something called the cosmic string, which has a lot of mass associated with it. And there were attempts to look for gravitational lensing on where they thought that was. But in order, if it was a string, then they could do that. When it's just like a long string of galaxies, the lensing is much weaker, and so they don't find that. But yeah, that's one way in which they tried to find if that was a real thing or not.
So they haven't really figured it out.
No, there's still a lot of debate as to even whether it's real or not. Okay, but there's something out there, but it's not nearly as big as they thought. Oh, just speak up.
Are radio waves bent the same way and to the same extent as light waves? Do they have the same energy?
They're all going to be bent the same way, and because what's most important to determine the bending is not the energy of the wave or what's being bent, but what's doing the bending. It's just like if I fall or I drop a small rock, we fall at the same rate. The acceleration of gravity on the Earth is the same, whether we're big or small. That's what, who was that? Went up in the Tower of Pisa and dropped a big rock and a small rock, right? So gravity waves, radio waves, all those things will all be bent by the same amount. And that's one way in which you can try to check to make sure that this is really due to lensing, to look at all the different wavelengths. So yeah. Yeah, speak.
Prior to understanding gravitational lenses, did we interpret those arcs and strings as having any mass at all?
Yeah, there was only a little while in which they didn't, there was a time difference between when they thought it was a real object and when they decided that was lensing.
So we didn't interpret them as having mass. We may not. Is this telling us that there may be more mass in the universe than we suspect?
Well, it would kind of be the opposite. It might tell you there's a little bit less, because you get more light from those objects, and you might want to say that because there's more light, there's more mass associated with them. But it's not the case, because the extra light that you get is just because of a lens rather than the fact that there's more stars producing it. But it's a really small effect, so it's not going to confuse them too much.
Concept, same concept they used to try to prove the existence of black holes?
No, the existence of black holes is more, they try to, basically some of the smaller black holes, they've tried to look at binary star systems. And in a binary stars, the two stars kind of go around each other. And so what they try to do is find a binary star where they see one star going around nothing. And that's usually, they can find some of those by X-rays, okay? Because as the objects fall into the black hole, they produce a lot of X-rays. The other way in which they do that is to look at the centers of galaxies. You know, the Milky Way galaxy has lots of stars, and it's thought that in the very center, a lot of stars should be compiled up together, and you put a whole bunch of these things together, and you can make a black hole. And you do look for those types of objects inside the centers of galaxies, but not necessarily by lensing effects. It would be nice, because that would give you the best way to determine the mass. But because those black holes are in the center of the galaxies, you can't really see any kind of lensing. But there are ways in which people are looking for dark halo objects by looking at lensing of, they monitor stars and look to see if stars get brighter and fainter periodically or non-periodically by objects that are kind of like black holes in the halo. That might be one way, if that's what you're thinking about. They do that way. Like they look at the Magellanic Cloud and look at all the stars, and hopefully if there's little tiny black holes in the halo of the Milky Way, they will do this kind of effect where make stars bright for a little while, and then as it moves away, then faint. Kind of like almost like that movie. Okay? And that is one way in which they do look for black holes, yeah, in the halo.
Other questions?
Thank you, Dr. Lavery. In closing here, I want to thank the Continuing Education Department. Can you hear? Yes. Particularly Barb Hagstrand, who is the lovely lady over here at the far south. Barb, please stand up. Thank her for arranging all this for our class here at MCC. And I would also like to point out one of my students, she and her husband has taken some pictures of the comet here recently. Debbie, do you have those back there on the? They're back there on the table. Those of you who haven't seen that, we'll take a look at some good amateur photography. And again, we want to thank Dr. Lavery for coming over and talking to us about gravitational lenses. I'm sure he'll stand around here a little while and discuss some things with you if necessary. But let's give him a round of applause again.
Well, I think it was too much.